Well, thanks for joining us today, James.
My pleasure.
So you've been talking a lot lately about the 4 trends that are helping to drive the greater use of parallelism. Can you walk us briefly through what those trends are?
Oh, absolutely. So, I have this great opportunity to sort of set up a day where speakers are going to be talking about detailed tools and detailed capabilities and how do you sort of make sense of it. So I talked about 4 trends that I see that are really helping make parallel programming more practical, more widespread. The 4 trends were better tools for software developers, better programming models for software developers to utilize for abstractions, more parallelism in the hardware itself, and finally opportunities or understandings on how to better educate ourselves as software developers in parallel programming.
Let's take each one of those individually, maybe a couple of minutes on each one. So better tools for parallel programming. What specifically we're talking about?
Yeah, so for software developers, the tools that we use, the compilers, the analysis tools, debugging tools, they benefit from parallelism too. This is an interesting point that it doesn't occur to us all the time to think about, but as computers are getting more and more powerful, the tools themselves can get more powerful. So what we've seen is tools taking advantage of that. So things like compilers that can do more analysis or can implement more features for parallelism, such as OpenMP or Silk Plus, or libraries that can do more things automatically in terms of adjusting and taking advantage of parallelism. Debugging tools, our inspector tool that can find race conditions, deadlocks, or memory leaks. And then finally, tools like vTune that can show you what this new found parallelism capability is actually doing in the hardware, can show you where you're waiting on locks, or can show you where performance bottlenecks are. All of these things you could easily forget about. You could forget that the tools are improving and think that the situation is the same as it was 5 years ago, but that'd be a big mistake. The advances in tooling to help with parallel programming are quite substantial.
Do you still run into companies or individuals using homegrown solutions to try to accomplish some of what is possible with today's parallel tools?
Yeah, well, of course we do, but it's really gotten to be less and less so. I think the advances in hardware and the advantages of taking advantage of the new hardware capabilities are so substantial that homegrown tools tend to be very inefficient. They don't keep up as well. It's a lot of work to maintain them. They certainly exist, but they need to be pretty high value add, and as parallelism has come on, a lot of early work that was done in-house on parallelism finally has the opportunity to use standard capabilities. To some extent, people that have interest in this really early have to develop some of the things themselves, but they eventually come on board when it becomes more standard, and they can just take advantage of something that another company or an open source project is producing and maintaining, and they can set aside the tools that they may have made 5 or 10 years ago to solve a problem nobody else was solving. They can put those aside, perhaps put their energy into new tools to solve things that the industry is not addressing today.
You have, we started to talk a little bit about a couple of the elements of your item number 2, threaded building blocks and Silk Plus. Can we talk a little bit more about how abstraction in general is helping advance the use of parallelism, and perhaps just a little bit about each of those particular tools?
Yeah, absolutely. So parallel programming models or abstractions to help take advantage of the hardware are really important. It used to be, if we were talking about parallel programming, the first thing we'd talk about is creating threads, creating a P thread or a Windows thread, and then managing them and mapping your algorithm onto threads, onto hardware. And what's really happened is the right way to program, parallelism is to have an abstraction that you program to. So you write in terms of task, or you write in terms of your data parallelism, and then that's mapped onto the hardware by the abstraction. So Intel threading building blocks is a great example. You try to create a lot of tasks, you create a parallel 4, but you don't worry about which iteration is being run on which core. That's handled by the runtime very efficiently, and that load balancing gives a lot of advantages. OpenMP does similar things. In some cases, not quite as well, because OpenMP doesn't address nested parallelism well. It was one of the mistakes we made in how we specified it. We underestimated the importance of that. So abstractions that have come later, such as threading building blocks or Silk Plus, and there are others that have take advantage of nested parallelism quite well. They're more composable. So OpenMP is extremely important, don't get me wrong, but it fits well in the domains that it's been successful in. But as we go further and we want to have other types of codes on board, these other abstractions have really filled in. So I think today, if you're programming in parallel, to do parallel programming, you're going to want to use one of these abstractions, these parallel models, and that frees the programmer, instead of worrying about how to map to the hardware, it frees them to express their algorithm in terms of parallelism, and that, again, boosts their productivity and so makes parallel programming more practical.
And just briefly, you talked about how Silk Plus is meant to help C programmers in this process. Can you just give us a capsule about why that's the case?
Yeah, it's a really important point. As successful as Intel Threading Building Blocks has been, which is a C++ template library, it sort of left C programmers high and dry, because C programmers aren't going to be using necessarily a C++ compiler, and even if they are, they aren't that interested in using templates. Templates is a very C++ idea. So C programmers with Silk Plus have a keyword-based approach that it works equally well in C and C++, but it really looks like C code. And so it's a huge advantage to be able to slip into a C program something that really fits in that world, and Silk Plus fits better in that world than TBB does.
Number 3, wildly more hardware parallelism.
Yes.
Wildly more.
Yes, wildly more. Well, you know, I started talking about parallel programming more broadly when dual core came out. And trying to get people excited about 2 cores was a challenge, because you could get up to 2x the performance if you were perfectly parallel, and in practical terms you rarely saw a 2x, so maybe you're only getting a 50% performance boost. Well, that's exciting, but not exciting enough. In fact, I was talking to a professor last year about teaching college students, and he emphasized to me that he needs big servers. He needs his students to see 16 or 32 cores to get excited. And I said, well, I laughed and I said, it's not just the students, it's all of us. So, you know, as we've marched through, we've seen 2 cores go to quad core, go to 8 cores, and in a lot of highly available processors now. But and that's starting to get pretty interesting. But now you see something like Intel Xeon Phi coprocessor with 61 cores. That's a lot of parallelism, and if you're just writing a serial program, you're leaving a lot of performance on the table. So I would say that the excitement around getting a parallel program working and the enormous performance benefits is pretty solid there. You know, your program may not be parallel all the time. That's another problem. So if you're only speeding up part of it on a dual core 2x, but you've got this big program, the speed up overall is so small. But now with 61 cores, you may get some parts of your program speeding up a few dozen x times or whatever, and with that capability, and even spread across the whole program, you can feel the difference. So this, and it's, of course, we're going to continue adding more parallelism to the hardware, but I think we're really at a point now where the amount of parallelism available in the hardware has gotten interesting enough that it makes it more interesting for a wider variety of applications, because you can get so much speed up out of a specific part of your program that you actually feel the difference.
Seems like a new challenge will be for programmers to get enough to really use all that parallelism.
Absolutely.
Available in the hardware. You're really up the ante. For people who just might be getting their heads around the difference between the chips, so can you tell us in miniature what a Xeon chip is best for and what a Xeon Phi chip is best for?
Certainly. So you know, Intel has a variety of different microprocessors, Atoms and Core processors and Xeons. And I tend to say Xeon a lot, but in all those cases, what we have are general purpose processors. In the case of a Xeon processor, it has the extra attributes of being highly available, ready for server environments, really industrial orientation. But in the case of all of these general purpose microprocessors, they're designed to balance between being able to run any application well, whether it be a fairly serial application or a bunch of serial applications or a mix or a parallel application. The processor has lots and lots of functionality in it. Well, when you make something that general purpose, even though it's wonderful and delightful to use, in engineering terms, you've probably given up something. And in this case, you've made the processor a little bit bigger, a little bit more power hungry, so it solves everything. And so we ask a different question. What if we designed a processor just to be good at parallel programs? Forget how terrible it is at a serial program, one that has no parallelism in it, just for parallel. And that's what Xeon Phi is about. The Intel Xeon Phi coprocessors are made up of a bunch of cores that are designed together in such a way as to excel at running a parallel program, but to really just ignore how good they are at a serial program. It's not quite that bad, but you would never buy an Intel Xeon Phi coprocessor to run a serial program on. You may run some serial programs because you have to get some housekeeping done, but you're going to buy it and use it for parallel. And so it sets up an exciting new product line that excels at parallel programming, but you really don't want to use it if you want to run, say, a general server workload or something on it, because it's really designed just for parallel programming, and it can take that to new heights. So now we have these complementary products, a Xeon and a Xeon Phi coprocessor, the Xeon processor being general purpose, the Xeon Phi being more specific to parallel workloads, and it gives our customers more options.
Makes sense. And the last of your four pillars, better educated programmers. So.
Yeah, absolutely. I think you don't want to forget that parallel programming is new in a lot of ways. The idea of it being so available and so important to so many people, you start wondering, what are the best teaching methods? And traditionally, parallel programming has been taught at a graduate level in college, and taught by people who are very excited about this idea of designing the hardware in parallel. And so you really spend a lot of time learning the hardware, and then how would you program this optimally? But that's not how we teach programming in general. We usually teach parallel programming by we usually teach programming by teaching programming constructs, what works. We teach concepts like linked lists and sorting algorithms and things. We don't emphasize the hardware design to start with. Goodness, how many people learn Java and know anything about the hardware? Usually very little. They just program. So I think one thing I'm real excited about is there's been a trend towards learning more about how to just teach parallel programming as parallel programming, not as motivated by the hardware. And a couple of co-authors, Michael McCool, who helped found RapidMind, or was the founder of RapidMind, Arch Robson, who designed and was the architect of threading building blocks. The three of us got together and wrote a book last summer that came out called Structured Parallel Programming, and tried to embody these concepts of how do you teach parallel programming without trying to motivate it all by the hardware. Yeah, we mentioned hardware a little bit in it, but only to mention that there are some concerns about locality that will affect your performance, and try to explain those. And by the way, I love computer architecture and go on and on about it, so it was really tough writing a book and not writing a few chapters in computer architecture, but I think that's important. And then we also learn with like the Xeon Phi. I just had a book come out in the last few weeks with my co-author Jim Jeffers on programming for the Intel Xeon Phi coprocessor, and the book's really about parallel programming. It's because the Xeon Phi has this 61 cores. The heart of teaching that is to explain, well, you really need to get your parallelism right. You need to have a program that scales, and you need a program that vectorizes. So the book really is, even though it says Xeon Phi in the cover, almost all of it's just general goodness about parallel programming. Yeah, it's very widely applicable, and if you use the techniques that are in the book, your program on a Xeon or a Core processor or even an Atom is going to run faster.
And that's available now?
It is available now. It is shipping. I've seen copies around today that people have gotten from Amazon and other places, and I gave away my only copy yesterday, but I'm looking forward to finding another copy for myself as an author.
Maybe we'll do a little book signing later.
There you go.
James, thank you very much for your time. Pleasure as always.
My pleasure.